Okay, so um, internal resistance. So what would happen if you were to take a battery and you were to just set it up like this? So here's my, I'm gonna draw a battery. Here's my copper top, TM, and I take a wire and I do that with it. Okay. Now let's imagine resistance equals 0. We know that's not true. There will be a very small resistance there, but let's just say the resistance in the wire is 0. What happens if we connect one terminal of the battery with the other? Well, we know this, right? V equals IR, or I equals V over R. What if that approaches 0? What does this approach? Now, does it make sense that you could have an infinite current, and let's say this is a blade, an infinite current out of a battery? Does that compute? Has anyone ever done this, by the way? It's hot, eh? Smokes, yeah. The thing is, there's not 0 resistance, but it's actually true that there's some resistance within the battery itself, okay? Batteries are made of chemicals. There has to be a flow or transfer of electrons through them, and of course, there's going to be some resistance going on within there, okay? So we're going to quickly mention internal resistance, and it's just this. Okay, so there's a special kind of a symbol that they use. I just want to double check what it looks like. I think it's a little curly E. EMF. Why am I not seeing it? Huh. Okay, hang on one sec, guys. This one. Yeah, so basically it looks like this. So you might measure. Oh dear. You might measure voltage across here. Okay. Like let's say we just do this, and let's say we put a voltmeter here. Okay. We're going to get 1.5 volts there. Okay. But that's not actually the electron motive force coming from the battery. In other words, that's not the total potential across the battery, because the thing is there's some little minuscule resistance just across the inside of the battery itself. So in reality, the true voltage of the battery, the true EMF of the battery, EMF is electron motive force measured in volts, is a little bit higher than 1.5 volts. Okay? So E, the electron motive force, okay, so we know that V equals IR, right? Well, now we're calling V EMF, and it's going to be higher than the voltage measured across the terminals of the battery. And where that's going to come from is it's going to come from IR, being the current through the circuit, or leaving and coming back into the battery, plus whatever resistance is in the battery itself. So big R, plus current across the internal resistance of the battery. Okay? So then you get a formula that looks kind of like this. See, I guess basically what this is doing is explaining why we don't get an infinite current here, even if we were to connect these together, and that's because power supplies themselves have a little bit of resistance inside of them, very small usually. Okay. There's also some other interesting things that we'll see a little bit later, like electric motors, for instance, as they're spinning, they're actually pushing power back against the flow of current through them. That's also called internal resistance, but this is the internal resistance within a battery. So, like, for example, we could just say battery has an EMF of 1.7 volts, a 0.5 ohm resistance is placed in circuit, and we could say the battery has an internal resistance of 0.05 ohms. Calculate the expected current. Okay, so essentially it's just like adding another resistor in series with this guy. So I equal to E over R plus little r, 7 volts divided by 0.5 ohm plus 0.05 ohm. And if we kind of do the math there, get about 3.1 amps. Okay? Does that make sense, guys? Right.